Welcome to the second half of algorithm design. My name is Ray Fan, and I'll be your instructor. So in the previous few lectures, we looked at problems which are NP-complete or p-space complete. And we saw that it's unlikely that we can solve these problems in polynomial time in the worst case. However, there are many NP-complete problems which actually occur in practice. And so therefore, we cannot just give up and say that we can't solve any of these problems. Okay, we need to find some way to deal with NP-completeness. And so today, we're going to look at several problems where by considering special cases of these problems, okay, we can actually solve them either efficiently or reasonably efficiently. Okay, so the problems we're going to look at are finding vertex covers. We're going to look at some NP-hard problems on trees. We're going to look at a problem called circular arc covering. And then we're going to go back to vertex cover and look at the problem in bipartite graphs. Okay, so as I said, there are many interesting NP-complete problems that we actually need to deal with in practice. And so what NP-completeness says is that in the worst case, we cannot expect to solve these problems in polynomial time. Okay, but it doesn't say that all instances of these problems are not efficiently solvable. Right? So there could be certain special cases of these problems that we can actually solve efficiently. And as long as these special cases are reasonably interesting, right, then it's actually useful for us to find efficient algorithms for these cases. All right, so the first problem we're going to look at is vertex cover. And we're going to look at a case of vertex cover which can be solved reasonably efficiently. So let's first recall what vertex cover is. Okay, so we're given a graph G over here. Okay, and we're trying to find a subset of the vertices to cover the graph, to cover the edges of the graph. And so what that means is, for example, if we take, if we take a node over here, let's say node 6, okay? So this actually covers some of the edges in the graph. So these edges are the ones which are adjacent to 6, okay? So it's so node 6 is going to cover these 3 edges, all right? If you look at node 7, right, it's also going to cover this edge, but then it's also going to cover some additional edges. And now this vertex cover problem is that we want to find a subset of the vertices so that every edge becomes covered. Okay, so now if we look at the blue vertices in this graph, right, then we can see that these 4 vertices can cover all of the edges in the graph. Okay, so in fact, if you take any edge, right? So let's say you take this edge. Okay, well, this is being covered by node 10. If you take this edge, right, this is being covered by node 3, and so on. Okay, so these 4 nodes actually form a vertex cover of the graph. And now the vertex cover problem is that if you're given a graph and then an integer k, the question is it possible to find k nodes in the graph to cover all of the edges? All right, so vertex cover in general is an NP-complete problem. Okay. However, you can think about a special case where what if the k we're looking for is very small? Okay, so we're just trying to cover the graph with a small number of nodes, right? So that should make the problem easier, right? So for example, suppose k equals 1. Okay, so that means that you just want to find a single node which can cover all of the edges in the graph. Well then, in order to solve that problem, all you need to do is just go through all of the nodes in the graph and see if any of them can cover all of the edges, right? And if there are n nodes on the graph, that would basically take you something like n squared time, because you need to consider every single node, right? And for each node, you need to check all of its neighboring edges, and then there can be up to n edges for that node. Okay, so altogether, you can run this in order n squared time, and you can see whether you can solve vertex cover for k equals 1. And you can generalize this to larger k by looking at, if you're trying to cover the graph using k vertices, then you can look at all subsets of k vertices out of your n nodes. Okay, so this would be the brute force approach of solving this problem. And the complexity for this brute force approach would be that, well, first of all, we need to consider all subsets of size k. Okay, so the number of subsets is going to be n choose k, right? And this is going to be order of n to the kth power. And then for each of these subsets, right, we need to take order kn time to check whether that subset is a vertex cover or not, right? Because we need to go through all of these k vertices, and for each vertex, we need to check all its adjacent edges. And there can be up to n adjacent edges. Okay, so altogether, this brute force approach is going to take us k times n to the k plus 1 power amount of time to do. All right, and now this approach is going to be very bad even for small values of n and k. Okay, so if we try n equals 1,000, and if we try to cover this graph using only 10 vertices, right, then we see that this brute force approach is going to take 10 to the 34th computations. Okay, and this is completely infeasible for any kind of computer that we have today. Now, what we're going to do is we're going to try to look for another algorithm, which is going to be much faster than the brute force algorithm. Now, this new algorithm is still going to be exponential time in the worst case, okay? But it's going to have a much better exponential dependency. So in particular, the brute force approach, right? So the exponential part involves both n and k. And what we want to do is we want to come up with an algorithm where the exponential part is only going to be something like 2 to the kth power. Okay, so we don't have this factor of n sitting in here. Okay, and we're going to see that even though this is still an exponential running time, it's going to be much, much faster in practice than the pure brute force approach. So for example, if you use n equals 1,000 and k equals 10, right, then this new approach is only going to take something like 10 million steps, okay, which is quite feasible. So in fact, for any small constant k, right, small value of k, or if k you consider that to be a constant, right, then this algorithm is going to be a practical algorithm. Okay, so the way we're going to design this algorithm is based on this key observation here. Okay, so what it's saying is that suppose you have a graph G, and then you take any edge u, v in this graph. Okay, now if this graph actually has a vertex cover of size k, okay, so we can actually find k vertices to cover this entire graph, then either this graph G minus u or G minus v. Okay, so I'm going to define for you what G minus u and G minus v are later. But one of these two graphs, G minus u or G minus v, is going to have a vertex cover of size at most k minus 1. Okay, so if G has a vertex cover of size k, right, then either G minus u or G minus v is going to have a vertex cover of size k minus 1. Right, and the converse also holds. Okay, if one of these two things, G minus u or G minus v, has a vertex cover of size k minus 1, then G is going to have a vertex cover of size k. Okay, so now first of all, I need to show you what this G minus u and G minus v are. Okay, so let me just give you an example here. So let's draw a graph like this. All right, so all right, let's draw a few more edges. All right, so now suppose this is node u here, and this is node v. Okay, so now G minus u, okay, this is simply the graph. So here we have the graph G, okay, and then G minus u is simply this graph, except for you're going to take out node u, and you're going to take out all of the edges adjacent to u. Okay, right, so this is going to be G minus u. Okay, oh, we need to take out u also. Right, and then likewise, G minus v is the same thing, except for you take out node v and all of its adjacent edges. Okay, so that would be so this would be G minus V. Okay, so yeah, so that is the claim, right? And now to show the claim, so first of all, so the first direction, we're going to show that. So let me actually draw back the original graph over here, right? So this is going to be a node V over here. So for the first direction, suppose G actually has a vertex cover of size K, right? Then this vertex cover has to cover this edge UV over here. Okay, and the only way to cover this edge is to either use node U or use V, or you can use both nodes if you want. Okay, but you have to use at least one of them. Okay, so suppose the cover actually includes the node U. Okay, so then yeah, so suppose the cover is called S, right? And then S is size K, so there are K vertices in S. Okay, now assume that U actually belongs to S. Now let's take node U out, okay? So now once you take node U out, right, so we're taking out one vertex from S, but then for the remaining graph, right, that must be covered by the rest of the nodes in S, right? Because we've already taken out U, and U cannot cover any of these remaining edges in G minus U, right? So the other vertices in S minus U must be able to cover G minus U, okay? And now, since S has K nodes, right, and you take one out, then we see that there are K minus 1 nodes that can cover G minus U. Okay. Now, if actually V was inside of S instead of U, right, then we would have that S minus V would be a size K minus 1 vertex cover of G minus V here. Okay. All right. So now we've shown the first direction. And the other direction is simply that, suppose S is a vertex cover of size of this G minus U, okay, and it's got size K minus 1, right? Then if you simply add node U over here, right, then that allows you to cover all of G, right, and then it takes you K nodes to do that. Okay, so we've shown both directions now. All right, so that's one property that we're going to use. The other property is that suppose G actually has a vertex cover of size K, right? Then the claim is that this graph has at most K times m minus 1 edges, okay? And the reason is simply that, well, since you have a vertex cover of size K, right, then if you take all of these nodes, these K nodes, right, each one of them has at most m minus 1 edges coming out of it, right? And if you take all of these edges from all of these vertices, right, then that allows you to cover all of the edges in G because you have a vertex cover. Okay, so that means that in total, since each of these nodes has only m minus 1 edges coming out of it, then in total this graph has at most K times m minus 1 edges. All right, so now we have both of these facts, and now we can actually use them to design an algorithm to solve vertex cover in this better exponential time that we talked about. So the algorithm is going to be like this. So we're going to phrase this algorithm recursively. So the two base cases for the recursion are, well, if G doesn't have any edges, then of course you can cover it, right? So then we can return true. And then on the other hand, if G has more than K times n edges, okay, then we know that if there is a vertex cover of size K, G cannot have, cannot have that many edges by the previous claim. And so therefore we can return false, right? And otherwise, we're going to use the first claim that we had. So we're going to pick any edge UV, okay? And then we're going to try to cover G minus U using K minus 1 vertices, okay? We're also going to try to cover G minus V using K minus 1 vertices. And what we said was that if there is a way to cover G using K vertices, then one of these two things must be possible, right? So then we're simply going to return A or B. Okay, so that means that if either A or B is possible, then we can cover all of G using K vertices. And if A and B are both false, right, then we cannot cover G using K vertices. Okay, so so this shows that this recursive algorithm works correctly. right? And now we're going to look at the time complexity of this algorithm. So the time complexity, basically, the way to see this is that here one of our input parameters is k, all right, and then we're going to make two recursive calls with parameter k minus 1. Okay, and now each of these recursive calls is also going to make two more recursive calls with parameter k minus 2. All right, so in total we have in order to execute this function with parameter k, we have two calls with k minus 1. We have 4 calls to this function with k minus 2, right? We're going to have 8 calls with k minus 3, and so on. So you see that the number of recursive calls is going to grow exponentially. Okay, so another way to see this is that we can actually draw out the recursion tree, right? So initially we have we call the function with k. That's going to create 2 recursive calls with k minus 1, 4 recursive calls with k minus 2, and so on. So in general, we're going to have to go down k levels of recursion. And so that means that at the very bottom level, right, we're going to have 2 to the k number of calls. Okay, and at each layer of the recursion, it's going to take us c times k times some constant c times k times n amount of time to check whether we have a vertex cover using some particular set of k nodes or not. Okay, so we have this recursion for the overall complexity, and then if you solve this recursion, you're going to see that the overall complexity is going to be 2 to the k times n. All right, so this shows that at least for small values of k, small vertex covers, we can actually solve a vertex cover in a reasonable amount of time. All right, so then for the next problem we're going to look at, so this is going to be, we're going to look at how to solve certain NP-hard problems on trees. So, so the problem we're going to focus on initially is going to be called independent set. So independent set, again, this is a graph problem, and we're trying to find a subset of nodes, and we want to look for nodes which are independent. And so what that means is that a set of nodes is independent if for any edge we do not include both endpoints of the edge. Okay, so for example, if we want to find an independent set on this this graph, right? So we can, for example, pick this node. But once we pick this node, then for any edge adjacent to this node, we cannot pick the other endpoint. Okay, so for example, we cannot pick this node over here because that would no longer be independent. Okay, however, we can pick, let's say, this node. Okay, and we can pick this node and this node. And let's say we also pick this node, right? And then we can pick this node. Okay, so these nodes are independent of each other, right? Because for any edge, we do not pick both endpoints of that edge. All right, now, of course, it's easy to find small independent sets, right? Because if you don't pick any of the nodes, well, that would be an independent set. Okay. And then as we try to find larger and larger independent sets, then the problem gets harder. Okay, so this independent set on trees problem is for us to find the biggest, so we're given an input graph, which is a tree, and we want to find the biggest possible independent set. Okay, right. Okay, and the way we're going to solve this problem is, again, it's going to come down to this, this key observation. Okay, so the observation is that, so first of all, in a tree, we have nodes which are called leaves, right? And the leaves are simply nodes with degree 1. So for example, this node is a leaf, right, because it's got degree 1. Okay, this node is not a leaf because it does not have degree 1. Okay, so we have all of these leaf nodes over here. All right, and the observation is that if V is a leaf, okay, then there is a maximum size independent set which contains V. Okay, so since we're looking for this maximum size independent set, right? Then if we have a node, if we have a node v which is a leaf, then we should definitely include that node. Okay, so this is what it's saying. And in order to prove this statement, well, suppose you actually have a maximum independent set S. Okay, now so we're focusing on a node v which is a leaf, and if v is already in S, then of course we're done. Okay. Now, on the other hand, if u is a neighbor of v, okay, so then, for example, here, well, actually, let me do it this way. Let me erase all of these. Okay, so now we're focusing on this node v over here, right? And let's say that uv is an edge. Now, if both of these nodes are not in the independent set, okay, both of them are not in S, right? Then we can actually include v in S, right? Because the only case where we cannot include v is if u is already in S, right? That prevents us from including v. But here, if both u and v are not a part of S, right, then we can include v, right? And then now we've made this independent, now we still have an independent set, right? S union v is still independent, and it's larger than S. Okay, so that would be a contradiction because we assumed that S was the largest size independent set. Okay, so we cannot have the case that both u and v are not in S. Okay, so so the final case is where u is in S but v is not in S. Okay, so suppose you currently you have some sort of independent set where u is currently in the set and v is not. Okay, well now we can actually take u out. Okay, if we take u out, we still have an independent set, and we're going to add v in. Okay, we're gonna take u out of S and we're gonna add v into S. And now this is still an independent set, right? Because the only edges which can conflict with u, the only nodes which can conflict with u are, well, what I'm trying to say is that by adding v, okay, we cannot possibly conflict with any other vertices, right? Because the only neighbor of v is u, because v is a leaf. Okay, so we can definitely just take u out and add v in, right? And now this new set, right, S minus u plus v, right, this has got the same cardinality as the original set S, and it's also independent. Okay, so this shows that there's always going to be a maximum size independent set which includes this leaf node v. Okay, any leaf node v. Yeah. So by the way, I want to mention that this is an example of these exchange arguments that we looked at. Okay. So remember, the exchange argument was to say that if you have a certain solution right now, then I can I can perturb that solution and I can get it into a more regular form that I'm happier to deal with, right? Just by sort of taking something out of your current solution and then adding something new into it. Okay. So by doing this exchange. Okay, and then I don't lose anything. I don't lose optimality by doing that exchange, but I make the solution have become more structured, and so it makes it easier to prove the algorithm is correct. Okay, so yeah, so then we have this observation, and then now we're going to use this to derive an algorithm. Okay, so so this is going to be a greedy algorithm. And then it's actually going to be looking for a maximum size independent set in a forest. So remember that a forest is just a collection of trees. Okay, so it's multiple trees. So previously we were looking at just one tree. Okay, but we can actually design an algorithm which can work simultaneously on a bunch of trees, a forest. Okay, so the way this is going to work is, so we're going to build up this independent set S. And initially, there's nothing in S. Okay, and what we're going to do is, we're basically going to be trying to add leaves into this S. So then we are going to look for an edge, UV, where V is a leaf. Okay, and then we're going to add, and then since we know that, the maximum size independent set is always going to contain this leaf, then we can just go ahead and add v into S. Right? And then once you add v into S, right, then you cannot add u into S anymore. Okay, So then we basically, at that point, we can eliminate U from S. And if you eliminate U, then you can also take out all of the edges adjacent to U. Okay, so just to give an example, right, and then before the example, and the so then we keep doing this, right? So we added this leaf V, right? We deleted the neighbor U and all the adjacent edges, right? And now we take another leaf, right? And then if the leaf has a neighbor, then we're gonna delete that neighbor and all the adjacent edges, and we just keep repeating this until we've deleted all of the edges. Right, so as we run this algorithm, we keep taking out more and more edges. So eventually, we're going to end up with no edges in this forest. Okay, and then we're going to return the S that we get from this process. So as an example of this, right? So suppose initially we're going to start with we can start with any leaf, but let's start with this leaf V over here. Okay, so then once we've added this node V, right? Then we're going to eliminate the neighbor U and all of the adjacent edges to U. Okay, so that's going to leave a bunch of these other vertices, and now we can also add in this vertex, right? Because this vertex now is not adjacent to anything because we've taken out this edge over here. Okay, all right, so now we can go for another leaf. So let's say that we go for this leaf, right? So we take this leaf, we remove the neighbor and all its adjacent edges. Okay, now we can take another leaf, let's say this one, right? So we can remove the neighbor, all the adjacent edges. And now we can also take this leaf, right? Because it's not adjacent to anything. We can take, so now the only nodes we have left, so we have these 4 nodes left. We can take this leaf, take out this node and all its adjacent edges. And then we can also take, so now both of these nodes at this point are leaves. And so we can actually take, let's say, this one. Okay, so in total, we've managed to take, what is this? 1, 2, 3, 4, 5, oops, right, 6, 7. Okay, so, oh, right, so sorry, when you take 2, right, you need to take out all its neighbors. Okay, so in total, we found a independent set of size 7. All right, now this algorithm is going to be, it's a correct algorithm, and that's simply based on the fact that we have this observation here that whenever you have a leaf, right, you should include it in your independent set. And also, this algorithm can be implemented efficiently if you consider nodes in post order. So post order is, this is a way of traversing a tree, right? And post order is that for each node, we're going to process all of the children of that node before we process that node itself. Okay, so that's post order. And you can sort of check for yourself that if you process the nodes in post order, then you can actually implement this this algorithm over here in order n time, n being the number of vertices. Okay, so this is our independent set on trees. And next, we're going to move on to a somewhat more general version of this. So we're going to look at a weighted independent set on trees. Okay, so so weighted independent set just means that, so previously, we were just trying to maximize the total number of vertices that we included in the independent set. Okay, and now we're going to consider a case where each of the vertices is going to have a positive weight. And we're trying to find an independent set which has the largest possible weight. Okay, so as an example of this, so suppose you have a graph like this, right? Let's say like this. Okay, now in the unweighted case, the maximum independent set would be all of these 4 nodes on the outside, right? So we would have a maximum independent set of size 4. Okay. However, if these guys have weights, right? So let's give some weights to these nodes. So suppose this has a weight of, let's say, 10, right? And suppose all of these other nodes have a weight of 1, right? So now the maximum weight independent set would actually just be the center node over here, okay? Because its weight is larger than all of the other weights combined. Okay, so this is our problem. We're trying to find an independent set of nodes S which has maximum weight. Okay, so to solve this problem, again, this is going to rely on an observation. So the observation is that, so if you have an edge UV, okay, and suppose that V is a leaf node, then either the opt is going to include U, right, or it's going to include all of the leaf nodes incident to U. Now, the reason is that, if we choose to include U, okay, then we cannot include any of the other, if you include U, right, then you cannot include any nodes incident to U, okay, because otherwise it's not an independent set anymore, okay. However, if you do not include U, okay, then you might as well include all of the leaf nodes adjacent to U. Okay, so let's do an example of this. So let's try to redraw this figure over here. Okay, let's make this graph a little larger. Okay, so now suppose you have a node U over here and a node V over here. Right. So if you choose to include node U, all right, then you cannot include V or any of these nodes adjacent to U, right? Because you need to, because the nodes need to be independent. But if you do not include U, okay, then there's no reason not to include V. Right, oops. There's no reason not to include V and all of these other leaves adjacent to U, right? So we might as well, let's switch to a different color here. Okay, so we might as well include all of these nodes, all of these other leaf nodes in the independent set. Okay, now we don't really know what we should do for this node, right? Because this is not a leaf node. But for these leaf nodes, right, why would we not include them? Because if we include them, then of course our weight over here goes up. Okay, and then by including these guys, we don't prevent the inclusion of anybody else because we've already decided not to include U over here, right? And then these leaves are only adjacent to U. So by including them, we don't prevent anything other than U from being included. And we've already decided not to include U. Okay, so therefore we should include all of these leaf nodes. All right, so that is the, the reason this observation is true. And, and then once we have this observation, then we can use it to derive an algorithm. So this algorithm is going to be based on dynamic programming. So the way we're going to start is that we're first of all going to root the tree. Okay, so let's just pick an arbitrary node in the tree to be root, any node. Okay, so for example, this node R over here. So the reason we want to root the tree is because we want to talk about things like subtrees. Okay, so for example, once you root this tree, right, then you can look at the nodes in terms of how far away they are from the root node, right? And then now you have this concept of subtree now. So for example, if we take this node, right, so R here is our root, and now if you take this node U, right, then the subtree of U would be all of these nodes V, W, X, and then this node down here, right? This entire thing would be the subtree rooted at U. Okay, so now, so we have this subtree notion, and now we're going to define these two values, opt-in of U and opt-out of U. Okay, so U is going to be any arbitrary node in the graph, and opt-in of U is going to be defined as the maximum weight independent set of the subtree rooted at U, where U has to be part of this independent set. Okay, so for example, if we take this subtree rooted at U, okay, so then opt-in of U is going to say that we are definitely going to include U in the independent set. Okay, and then having decided to include U, now we're going to look for the maximum weight independent set in this subtree. All right, and then alternatively, we're going to have opt-out of U, right? And so this one is going to be, again, we're going to consider the subtree rooted at U, but here we're going to not include U in the independent set. Okay, and then we're going to look for the max weight independent set where U is not part of this, this independent set in the subtree. Okay, now once you define these two values, okay, then we can actually, we have some recursive relationships between these values. Okay, so the first, so the first relationship is that what is the value of opt-in of U? Okay, well, opt-in of U is we are going to include U, right? So we get a like WU amount of value from including U, right? So we include U over here, right? But once you include U, you cannot include any of its children, okay? Otherwise, you don't have an independent set. So therefore, we're going to take all of the children of U, right? And we're going to not include any of them. Okay, so for each child V of U, we're going to look at what is the maximum weight independent set you can have where you do not include V in V subtree. Okay, so for each of these subtrees, for each of these children of U, we're going to have one of these opt out of V values. Okay, so basically for this subtree, we're going to look at, well, if I force myself not to include V, what is my optimum value? Okay. Likewise, for this subtree, if I force myself not to include W, what is my optimum value, right? And then here, I don't include X, what is my optimum value? Okay, and then I did choose to include U over here, okay, right? So then my overall value is going to be WU plus the sum of all of these opt-out values. All right, that's where I choose to include U. Now, the next case is where I do not include U. So let's draw this over here. So if I don't include U, all right, then I have the option of including, then for each child of U, I have the option of including that child or not. All right, so then I'm going to go through all of the children of U, and then for each child, I can either include that child in its subtree, right, in the independent set formed from its subtree, or I can not include that child. Okay, I don't know which one is better. So I'm just going to pick the max of these two. Whichever one is better, that's what I'm going to do. Okay, so so we have these two recursive relationships for opt-in and opt-out. All right, now we can take this and then we can use this. We can now produce an algorithm for finding maximum weight independent set in the tree. Okay, so so the way we're going to do this is that we're going to root the tree arbitrarily at some node R. All right, and then again, we're going to process all of the nodes in the tree in post order. Okay, so post order means that, so I mentioned this, but post order means that we're going to visit all of the children of a node before visiting the node itself. Okay, and the reason we're going to process things in post order is because, you know, if you look at this this DP relationship over here, okay, so here we are saying something about the root of the about a large subtree, right? So let's say that you know, we're talking about U over here. Okay, so we're making a statement about this large subtree rooted at U in terms of smaller subtrees of the children of U. Okay, so this means that we actually want to process these smaller subtrees before we process the large subtree. Okay, so we want to process the children of a node before we process the node itself. And so this is why we're going to consider all of these nodes here in post order. All right, so in post order, the first nodes that we're going to consider are the leaves. Okay, and so if we, you know, so as we're processing this, if we're at a leaf, right, then so we want to compute these values, the opt-in and opt-out values. Okay, so in this code over here, right, we're going to call them, we're going to call these values m in and m out. Okay, now if U is a leaf, right, then now we're trying to form the maximum weight independent set on U, where U is a leaf. Okay, so then we have the rest of this graph over here, but U is going to be a leaf. And so, so here, if we choose to include U, right, then we simply get a weight of WU. Okay, and then if we do not include U, right, then we get a weight of 0. Right? So the MN and M out values for U are easy to compute, right? Just WU or 0. Right? Alternatively, if U is not a leaf, right, then U is going to have some children. So for example, if U is this node over here, right, then U has children. And in that case, we're going to be using these relationships from the previous page. Okay, so these relationships say that if we choose to include U, right, then we get a score of WU plus opt out for all its children. Okay, so that is being expressed over here, right? So we get a score of WU plus for all the children of U, we need to keep them out of the set. And then for if we choose not to include U, okay, then this relationship says that we should look at all of the children of U, right? And then we should do whichever decision is better. Either we can include that child or we can not include the child, right? And so here, yeah, so this code is going to do that. All right. So so this is so when we run this code, this is gonna, well, first of all, it's gonna work correctly because we are processing the nodes in post order, right? So that means that when you by the time you get to processing a node U, right, because we're going in post order, we've already processed all its children. So we already know all of these values for its children, right? Both M in of V and M out of V for all of the children of U. We've already computed those values, okay? And that allows us to correctly compute M in and M out of U. Okay, so then after doing all of this, right, then the final value that we want to return is that, so this entire algorithm is going to bottom out at the root node R, right? R is going to be the final node that we process, okay? And for this node, we can either choose to, for the root node R, we can either choose to include it or not include it in the independent set, okay? And we're just going to do whichever, we're going to make whichever choice gives us the larger value. Okay, so overall, we're going to return the max of these two values. Okay, so the overall time complexity for this algorithm is simply to do a post-order traversal, because at each node, the complexity at that node is just a constant. Right, for the leaves, right, we just we set two values here, and then for okay, so I guess it's order M. Yeah, sorry about that. So the complexity is actually going to be order M, because here you need to sort of sum over all of the children. Okay, so basically for each edge in the graph, that edge is going to be included in one of these sums. Okay, so altogether, the complexity of this is going to be M, order M, which is the number of edges. Okay, and also this algorithm over here only tells you what the final value for the independent set is, for the maximum independent set. Okay, it doesn't actually tell you what the independent set is, right? So in order to determine what the independent set actually is, right, we can just do backtracing. So remember that when we talked about dynamic programs, right, if you do, so backtracing means you need to keep track of which decision actually led you to obtain the optimum value. Okay, so here, right, we had to make a decision whether to include V or exclude V. Okay, so we can just keep track of those decisions, right, and then here we also have to make a decision whether to include or exclude R. Okay, so we keep track of all those decisions, and then and then that tells us how to actually produce this this maximum weight independent set. All right, so okay, so this shows that at least in trees we can actually solve this independent set problem, even though in general this problem is going to be NP complete. Okay, so now why is it that we can actually solve this problem efficiently in trees, whereas in general we cannot solve it efficiently? Okay, so the reason is that trees have a very special property, which is that for any pair of nodes, there's only one path between those two nodes. Okay, so another way to say this is that if we root the tree, right? So now if we look at a subtree, let's say a subtree rooted at U, okay, then if you look at all of the children of U, so each of those leads to a subtree also, right? So that's these triangles over here. Okay, now what we know is that because this whole thing here is a subtree, then there is no edge between any of these triangles to another triangle. Okay, so for example, there's no edge over here, right? There are no edges like that, okay? And because there are no edges between these different subtrees, then that means that we can actually we can process these subtrees independently. Okay, so any decision that we make in, let's say, the first subtree is not going to affect what we're allowed to do in any other subtree because there are no edges between these subtrees, and so there's no constraints, there's no consistency constraints between the different subtrees. And so that means that we can actually solve these subtrees independently of each other. Okay, the only constraints on these subtrees are if we make a decision for U. So for example, if we choose to include U in the independent set, okay, well then that's going to force us to do certain things in each of these subtrees, right? So for example, we cannot include the root of these subtrees if we include U. Okay, so the subtrees do need to be consistent with this root node U over here. Okay, however, there are no consistency constraints between the different subtrees, and so therefore we can solve them independently of each other. And because you can solve them this independently, this is what allows you to run that dynamic program that we just saw. Okay? Yeah, so in a general graph, of course, right? So if we're not in a tree, then in a general graph, there could be edges between these different subtrees, okay? And in that case, we cannot solve these independently because if we make certain decisions in this subtree, for example, right, and we make certain decisions in this other subtree, then due to these edges, these possible edges between the subtrees, these decisions in the subtrees have to be consistent with each other, right? And it's and this is what makes the problem hard, in fact, intractable. Okay, is to ensure this consistency between these different parts. Okay, but as long as we don't have these constraints, right, then we can just solve this independently. Now, this algorithm for independent sets, it works in trees. Okay, so trees are a very special type of graph. Okay. And it would be nice if we could expand this algorithm to something which is more general than trees. And it turns out that it is possible to, it is usually possible to do this, to expand these algorithms to a larger set of graphs, okay? And in particular, there's a type of graph called graphs of bounded tree width. Now, these graphs somehow look like trees, okay? So they're not exactly trees. So they're a wider class of graphs than trees. So trees are included in the set of bounded tree width graphs, but there are additional graphs in this class which are not trees. Okay, but even these additional graphs, they kind of look like trees in some sense. Okay, so yeah, I'm not going to get into too many details about this, but they, but at a high level, you know, if you take these bounded tree width graphs, you can kind of take subsets of the nodes in these graphs, okay? And you can sort of combine these subsets into, let's call this a super node, okay? So you have these, so now you can take the original graph, you take subsets of the nodes, and then you combine them into these super nodes, right? And now if you look at the edges between the super nodes, then these edges forms something that looks like a tree. Okay, so therefore these bounded tree width graphs, they're not trees on normal nodes, they're trees on these sort of super nodes. Okay, but they still have this overall tree structure. And because it's got this tree structure, then again, it's got this property that different subtrees can be solved independently of each other. Okay, so for the tree width graphs, you can apply something similar to the algorithm that we used for trees to solve for example, the independent set problem on graphs of bounded tree width can also be solved in time, which is going to depend on the tree width. So the tree width is basically, we said that there are these supernodes, right? So the size of the largest supernode, that is going to be the tree width of this graph, okay? And these bounded tree width algorithms usually have running times which are exponential in the tree width, but it's going to be polynomial in the other parameters of the graph, including the number of nodes and the number of edges. Okay, so as long as you have a graph with small tree width, then you can solve these problems efficiently on those graphs. And so, for example, trees have a tree width of 1. Okay, so you can solve these algorithms efficiently. You can run these algorithms efficiently on trees. Okay, one more thing I want to mention is that these algorithms, this algorithm, right, we only talked about how to do it on independent sets. Okay, but there are many other NP-complete problems or NP-hard problems that when you restrict them to trees, you can apply a similar methodology as what we used over here. Okay, so as long as you're working with a tree, then there's going to be these independent these subproblems that you can solve independently for whatever problem that you're talking about, right? It often decomposes into a bunch of independent problems which you can solve independently, and then you can combine these solutions in some sort of dynamic program to solve the overall problem. Okay, so this is not just a this technique that we looked at applies to more than just trees, and it applies to more than just the independent set problem. All right, so so moving on. So next we're going to talk about the problem of circular arc covering. Okay, so so let's introduce this problem first of all. All right, so we're going to look at this figure of this circle thing over here, right? So what we're going to have is we're going to have a just a cycle graph like this, okay, on n nodes. So here n is going to be 4. Okay, so we just have you know, this cycle thing over here, okay, and we also have a bunch of these paths. So a path is just going to contain some group of consecutive edges from this cycle. So for example, this one of these paths is going to be A, right? So A just contains the edge 4, 1. Okay. Now this path over here, B, right? This is going to contain edges 4, 1 and 1, 2. Okay. And likewise, like D over here, right? So this is going to contain edges 1, 2 and 2, 3. Okay, so we're going to have this situation where you have a cycle first of all, and then you have and the cycle has n nodes. Okay, and then we're going to have m paths on this cycle, where each path is going to start at some edge and start at some vertex, end at some other vertex, and it's going to include all of the intermediate edges. Okay, so in this case we have, you know, A through F, right? So we have 6 edges. Okay, 6 paths. All right, now what we're trying to do for this problem over here, for the circular arc covering problem, is that we're trying to make sure that whenever 2 paths have an intersection, we're trying to assign colors to these paths in a way that whenever 2 paths have an intersection, right, they have some edge in common, then these two paths have to be assigned different colors. So for example, this A path over here, right? This has an intersection with B, right? Because they both use this edge 4, 1 over here. And so therefore they have to have different colors. Okay, so in this case, A is going to be green and B is blue. Okay, likewise, let's say B and C, right? Well, they have an intersection because they both use the edge 4, 1 again. Okay, so they also have to have different colors. Okay, on the other hand, if you look at, let's say, path E over here, okay, so E is going to use 3 edges, right? 1, 2, 2, 3, and 3, 4. And this does not have any intersection with the A path. And so therefore A and E are allowed to use the same color. All right, so we're going to assign all of the paths colors, and we need to make sure that whenever they use a common edge, they have different colors. And then lastly, we're trying to use as few colors as possible. Okay, so in this case, it turns out that we can color everything correctly using just 3 colors. So this is the circular arc covering problem. Okay. All right, now let me talk a bit about the motivation for this problem, first of all. So this comes from some designing communication networks. Okay, so suppose you have a simple communication network where you have a bunch of points which might want to communicate with each other. Okay, so the points are these 4 vertices, right? And the connections between these points is simply this cycle over here. Okay. And now, suppose you have a bunch of communication streams between certain pairs of these vertices. So for example, maybe 4 and 1 want to communicate. Right? So in that case, we're going to make a path between 4 and 1. Right? If let's say 3 and 1 want to communicate, right, then we're going to make a path like this, right, the C path between 3 and 1. Okay, so we have a bunch of pairs of nodes that want to communicate, and for each one of them, we're going to set up a path like this. Okay. Now, some of these paths, now these edges over here, right, on this black part. Okay. So these represent actual communication links. Okay. So these are like actual wires in your communication system. And then if you have multiple communication streams that use the same wire, okay, then these different communication streams cannot be transmitted at the same wavelength. Because if you, I guess this gets into the design of these networks actually, but if you use the same wavelength for these different streams, right, then they're going to interfere with each other and you can't do the communication correctly. Okay, so the upshot is that we have a bunch of these streams whenever they use the same physical link. Okay, so whenever they have an intersection with each other, then they have to use different wavelengths. And we're going to model that by, we're going to assign like each wavelength corresponds to a color. Okay, so we're trying to use as few wavelengths as possible, and that corresponds to using as few colors as possible, where we have to ensure that streams which use the same edge, right, have different colors or different wavelengths. Okay, so that is the motivation for this problem. And now, in terms of complexity, so it turns out that this problem, while it doesn't look very complicated, this problem is also NP-complete. Okay, even though all we're trying to do is just basically color a ring, this still turns out to be NP-complete. Okay. Now, of course, in practice, when you're actually using this, because this does come from a practical motivation. Okay, so in practice, the situation you deal with is that you might actually have lots of these communication streams. Okay, so we have M streams over here, and M can be quite large. Okay, and then N, the number of nodes, can also be reasonably large. Okay, however, we usually don't have too much overlap between these streams. Okay, so the number of different colors that we're trying to assign to these different streams might be reasonably small. Okay, so we want to design an algorithm which can work efficiently in that case. Now, the basic brute force approach would just be to, for each one of these M streams, right, it gets one of these K colors, and so therefore we can just try all K to the M possibilities for all possible K colorings of these M streams. Okay, now this is not going to work well because M can be, let's say 1,000, right, and K is something like 10. Okay, so this is completely going to be infeasible. Okay, so instead of doing the brute force approach, we want something like this, where the complexity is going to be some sort of function of K. And this here can be an exponential function. Okay, so we allow this to be exponential because we assume that K is going to be small in practice. So even though this is exponential, it is still somehow feasible. Okay, but for the other parameters, for the number of streams and the number of nodes, right, we want the complexity to be polynomial. in the other parameters. Okay, so overall, we get an algorithm which is feasible as long as k is small, right? Because this other part here is not going to grow too fast. Okay, so to do this, we are first going to relate this circular arc covering problem to a problem that we've already looked at previously, which is the interval coloring problem. Okay, so just to remind you how the interval covering problem worked. So here we have a bunch of these intervals, okay, and then we're going to assign colors to these intervals, and the requirement is that if two intervals intersect with each other, they have different colors. Okay, so we looked at a greedy algorithm for solving this problem, right? Which was very efficient. Okay. Now the relationship between the interval coloring problem and this arc covering problem is that, well, you know, they're actually quite similar to each other in the sense that for this arc covering, right, we also have these paths which you can think of as intervals, right? And then whenever two paths intersect, right, so whenever these two intervals overlap with each other, we require them to have different colors, just like in interval coloring. The only difference between circular arc covering and interval coloring is that for interval coloring, right, we have just this linear structure over here, whereas for circular arc covering, we have a cycle, okay? And yeah, and it turns out that just, you know, this small change is going to make the problem go from solvable using a greedy algorithm, using a simple greedy algorithm, to being NP complete, okay? And basically, the reason this problem becomes much harder when we have a cycle is because for interval covering, we have this very nice property. We have this duality property where the minimum number of colors you need to color all the intervals is equal to the depth of these intervals, where the depth is like the maximum number of overlapping intervals at any time point. Okay, so for example, in this example, right, we see that we oftentimes have 3 intervals that overlap with each other, okay, and never more than 3 intervals. So therefore, the depth in this example is 3, right? And for interval coloring, what we have is that the number of colors, right, the minimum number of colors, is equal to the depth. And for circular arc covering, coloring, we have something similar but weaker. Okay, we have that the number of colors is at least the depth. Okay, so the number of colors can actually be larger than the depth, but it's never less than the depth. So just to give an example where the number of colors that you need is going to be larger than the maximum depth, right? If you look at this example over here, then the maximum depth at any time point, right, is always going to be 2. Okay. However, you see that it's going to take you at least 3 colors to color this this graph. Okay. Basically, because you know you can start out with, let's say you know, the blue and the red. Okay. But then eventually, so then that's going to force this this interval over here, right? So this interval has intersections both with the blue part and with the red part. Okay, so therefore it needs a 3rd color, right? Even though you know, when it intersects the blue part, it does not intersect the red part, and when it intersects the red, it doesn't intersect the blue, right? But you know, at different points along this green interval, it intersects both the blue and the red, and so therefore we need to give it a 3rd color. Okay, so therefore we don't have the strong duality for this circular arc covering. And so that means that we cannot apply the greedy algorithm for interval coloring to this arc coloring. Okay, but nevertheless, because these two problems you know, look so similar to each other, okay, we're still going to try to make use of the interval coloring problem in order to solve the arc coloring problem. Okay, and the way we're going to do that is we're going to convert arc coloring to interval coloring. And the way we're going to do the conversion is that So we have these vertices over here, right? So let's say that we have n vertices, right? N equals 4 in this case, right? Now, we're actually going to create one additional vertex between the first vertex and the last vertex. Okay, we're going to call this, let's say, v0. And we're gonna cut the cycle at v0. Okay, and what it means to cut the cycle is that if you have any path which crosses the cut, we're going to split that path into two paths. Okay, so for example, the C path here, right, it crosses the cut, so we're going to split this into two paths. Okay, like that. Okay, and we're going to call one of these, so we're going to give it a different name now. We're going to call this C prime. Okay, so it used to be just one path, right? So now we split it into two paths. We're going to call one half C prime, and the other half we're going to call C double prime. Okay, likewise, this B interval over here, okay? So this also crosses the cut, so we're going to split this into two parts. Okay, we're going to call one part B prime and the other part B double prime. And then the A part, the A interval also crosses the cut, right? So we're going to split this and then call the two parts A prime and A double prime. Okay, so now once you've made the cut, right, then now you can basically you can pull this cycle apart, right? So imagine that you just grab both ends and then you pull it apart. Okay, once you pull it apart, you're going to end up with this this thing over here. Okay, so what I mean by this is, for example, this C prime here, right? You see that C prime is gonna overlap with B prime and A prime. Okay, so just like in this figure over here, we have C prime overlapping with A prime and B prime. Okay, and likewise, you have this B prime interval over here, right? It's going to overlap with D and E. Okay, so we see this overlap between B prime and then D and E. Okay, right? So if you pull this interval apart, right, and then in the end, you see that we have this A prime. So we have, for example, this C double prime here. Okay, so C double prime here is going to overlap with what is this thing? E over here. Okay, so we have this overlap between C double prime and E, and then C double prime also overlaps with F. Okay, so you see that by taking this circle thing and cutting it, and then splitting and then pulling it apart, right? We actually get an instance of interval coloring. Okay, so now we're gonna so we know how to solve interval coloring. Okay, however, it's not enough just to solve interval coloring on this instance that we have, because what we need to ensure is that, well, since this A prime, for example, right? So this came from where did we get this A prime from? Well, we got it from taking this interval A and splitting it into two parts, A prime and A double prime. Right? So now A itself used to have just a single color. And so when you split this into A prime and A double prime, you actually have to make sure that both A prime and A double prime have the same color. Right? So whatever color A was given, right, you have to give that same color to both A prime and A double prime. Okay, so we need to ensure some sort of consistency between all of these prime and double prime intervals, right? A prime and A double prime have to have the same color. B prime and B double prime, they also have to have the same color, and then C prime and C double prime. Okay, so we want to interval color this this graph over here. However, we need to ensure consistency between these intervals, which came about by cutting. All right, so now how are we going to do this? Okay, well, the way this is going to work is that okay, so here I'm showing the interval color graph. Okay, and we're just gonna so because it's interval coloring, then now we can just go from let's say one end to the other. Okay, so let's say that we start at node V0, right? And we're just going to go through all of the nodes, 1, 2, 3, 4. Okay, so at node V0, we're going to look at which intervals actually overlap with V0. Okay, so that's going to be intervals A prime, B prime, C prime, right? And then we can color these arbitrarily. So let's just say that whatever color A prime gets, let's call that color 1. Okay, whatever color B gets, let's call that 2, and then C gets color 3. C prime gets color 3. Okay, so yeah, so initially we start out with this coloring, 1, 2, 3, right? And now we're going to move on to the next vertex. So once you move on to the next vertex, then some of these intervals are going to end. So for example, A prime and C prime, they both end at V1, right? But then you also have some intervals that continue. So like this B prime here, it continues through V1. Okay. Now, because B prime is continuing through V1, then the color that B prime gets at V1 has to be equal to the color that B prime gets at V0. Okay. So now here at V1, we're going to look at what are all the possible colorings of the intervals which intersect V1. So we have 3 intervals. We have E, B prime, and D, which intersect V1. Okay. We want to find all the possible colorings of these intervals. And again, since B prime, it was already given color 2 at node V0. So then once you get to V1, it has to keep the same color. It still has to be 2. Okay, so now, oh, I forgot to say this. So let's define a parameter K, where we're trying to answer the question, is it possible to color this arc using at most K colors? Okay, so this is what we're trying to answer, right? So in this case, K is going to be 3, and we're trying to see if it's possible to 3-color this arc, right? So so initially we give these nodes colors 1, 2, 3, and once you get to V1, then B prime is still going to have color 2, and the remaining colors are going to be 1 and 3, and you can actually assign these colors 1 and 3 to E and D arbitrarily. So for example, you can say that D gets color 1 and E gets color 3, right? Or you can give D color 3 and then E color 1. Okay, so we have 2 colorings here which are consistent with this initial coloring for A prime, B prime, C prime. Right? So we have two consistent colorings over here. Right? So now we're going to move on to the next node, and we're going to again look for colorings which are consistent with the coloring at the previous node. Okay, so we're trying to find all the colorings at V2 which are consistent with the colorings at V1. Okay, and to do this, well, first of all, so you see that at V2 we have this interval E, right? And E started at V1 and it continues through V2. So therefore, and the same thing for D. Okay, so both E and D start at V1 and they continue through V2. And so therefore, both E and D have to keep the same color at V2 as they had in V1. Okay, so that means that if at V1 we use the coloring 1, 2, 3 over here, right, then once we get to V2, we have to still color D using 1, and we still have to color E using 3, and so that means that the only color for F is going to be 2. Okay, so if we start with this coloring over here, we have to produce this coloring over here. Right. Alternatively, if we colored these 2 guys using 3, 2, 1, okay, instead of 1, 2, 3, then they have to keep the same colors at V2, right? E and D have to have the same colors at V2, and so they're still going to have colors. D is going to be 3 and E is going to be 1, and so again that forces F to be 2. Okay, so we see that at V2 there are only 2 colorings which are consistent with any of the colorings at V1. Okay, so we take all the colorings at V1 and we look for what are all the possible consistent colorings at V2. Okay, and there are 2 of them. All right, let's move on to V3. So V3, we see that interval E continues from V2 to V3, and interval F also continues from V2 to V3. Okay. And so therefore, E and F have to have the same colors at V3 as they had in V2. So that means that if we used color, this coloring over here, right? Then once we move to V3, right? E and F still have to be colored, 2 and 3, and so that means that this C double prime here has to have color 1. Okay, and likewise, if we used this coloring over here, right, then when you move to V3, you have to have these colorings, this coloring. Okay, yeah. So so at V3, there are also two colorings which are consistent with the colorings at V2. All right, and now finally we get to V4. Okay, so at V4, what we have is that we just have one interval, C double prime, which continues from V3 to V4. Okay, and the C double prime needs to have the same color both at V3 and V4. And so this means that if we used this coloring over here, where C prime had color 1, okay, then when you go to V4, right, you can either produce this coloring, right, where A prime and B prime, or A double prime and B double prime have these two colors, or you can have this coloring, right? So there are two possible colorings which are consistent with the first coloring over here, right? And then if we had the second coloring over here, right, then we would also produce two consistent colorings at V4, right? So as long as we color C double prime the same way, right, then we have a choice for E and F, or sorry, for A prime, A double prime, and B double prime. Okay, so so that means that at the end, right, at V4 over here, we actually have 4 colorings which are consistent with the possible colorings at V3, which are consistent with the possible colorings at V2, right, which are consistent with the colorings at V1, which are consistent with the original colorings. Okay? All right, now the final thing to do is to look at all of these, so I'm going to erase all of this stuff, right? And the final thing to do is to look at all of these permitted colorings. So these are the only possible colorings that we can end up with at V4, right? Because we need to have consistency among all of these intermediate colorings. Okay, and in order to ensure consistency, the only possible colorings at V4 are these 4 colorings that we end up with. Now, the final thing we need to check is, are any of these possible colorings, do any of these match the initial coloring for A prime, B prime, C prime? Because these colorings over here are the colorings for A double prime, B double prime, and C double prime. Okay. If any of them matches the coloring for A prime, B prime, C prime, right, then we have these properties. So remember, the property we wanted was for the coloring over here to match the coloring over here. Okay, if we can accomplish that, then we have a consistent coloring for the entire arc. Okay, so now we're just going to look through all of these 4 colorings over here to see if any of them are consistent with this thing over here. And indeed, we see that this coloring, right, this third one, right? So we see that A double prime here is 1, and then initially A prime was also color 1, right? And then B prime and B double prime are both 2, right? And then C prime and C double prime are both 3. Okay, so therefore we have a coloring at the very end which matches the initial coloring, and this means that it is possible to use 3 colors to color this entire arc graph. Okay, so this is a yes instance of this arc coloring problem using 3 colors. Now, if it turned out that for all of these colorings at the end, if none of them are consistent with the initial colorings for A prime, B prime, C prime, right, then that would mean that there is no way to color this arc using 3 colors. Okay. Yeah, so basically, what we needed to do was, we're going to start with this coloring, right? And then we're going to move to this coloring, right? And then that's going to move to this coloring, it's going to move to this coloring, and then finally to that coloring. Okay, and each of these colorings is consistent with the previous one. And so overall, we have consistency. Okay, so that is the circular arc coloring problem. Now, in terms of time complexity for this problem, what we have to do is, now suppose there are k intervals that cross some vertex. Okay, so in this case, we have 3 intervals that cross a vertex. right? So then what you have to do is you have to consider all possible colorings of these k intervals. And then you have to see if any of those possible colorings are consistent, any of these possible colorings are consistent with the colorings from the previous interval. Okay, and so the number of colorings, if there are k intervals that cross vi, then the number of colorings to consider is k factorial. Okay, because for the first interval, it has k possible colors. For the next interval, it's got k minus 1 possible colors, right? Times k minus 2, and so on. Okay, so so at each one of these vertices, right, we have to consider all k factorial possible colorings to see whether any of them are consistent with the colorings of the previous vertex. And we have n vertices in total, right? So therefore, the overall running time is going to be k factorial times n. Right? And this is so this accomplishes what we wanted to do at the beginning, which was that we wanted a complexity which is possibly exponential in k, right? But k is usually small, but it's going to be polynomial in the number of vertices. Okay. Yeah. So in fact, even if you set k to be 10, right? Then I'm not sure what 10 factorial is. I think it's like a few million or something, right? So this is still a reasonably feasible algorithm. Okay. All right. Okay, so we're going to move on to the final problem over here, which is we're going to go back to vertex cover. But remember that the first time we looked at vertex cover, we were looking for small vertex covers. Okay, and we saw that there is an exponential time algorithm where the exponent includes the size of the vertex cover. Right, now here we're going to look at vertex cover, but we're going to look for a polynomial time algorithm, but it's only going to work in bipartite graphs. Okay, we have no hope of actually getting a polynomial time algorithm for general graphs. So we're just going to focus on bipartite graphs. Okay, so remember that bipartite graphs are ones where you can you can take a set of vertices and you can split them into two sets. Okay, let's call them the left set and the right set. And the only edges in the graph are ones between the left vertices and the right vertices. Okay, so you don't have any edges between the left vertices, and you don't have any edges between the right vertices, but you could have edges between the left and the right vertices. Okay, and now we're trying to find a vertex cover in this graph. Okay, yeah, and so for example, in this example over here, right, a vertex cover would be these 5 nodes. Okay, 1 prime, 2 prime, and then 3, 4, 5. Okay, so the way we're going to do this is that we're going to look at some problems that we can actually solve efficiently on bipartite graphs, and we're going to try to make use of them. So one problem that we can solve efficiently on bipartite graphs is matching. Okay, so remember that a matching is just, it's going to be a set of edges where none of the edges share a common endpoint. Okay, so for example, you see that these 4 edges over here, right? So this is a matching, right? So none of them have a common endpoint. Okay, now the way so the nice property about matchings is that so the first property is this weak duality property. Okay, which is what it's saying is that if you take any matching, okay, and if you take any vertex cover, okay, then the matching is not going to be larger than the vertex cover. Okay, so here we have 4 edges in the matching. Okay, so the size of this matching is going to be 4, right? And then we saw that previously we had a vertex cover using 5 nodes. Okay, you could also have larger vertex covers, but what this is saying is that any matching is going to be no larger than any vertex cover. Okay, and the reason this is true is because if you look at a vertex cover, okay, each node from the vertex cover can only cover one edge from the matching, can cover at most one edge from the matching. Okay, because for example, suppose this node was in the vertex cover. There's no way for this node to cover 2 edges from the matching because these edges from the matching they don't intersect at any nodes. Right? All of these matching edges are disjoint from each other. So therefore, this vertex cover node can cover at most one edge from the matching. Okay, so and so that means that in order to cover all of the edges in the matching, right, we need to have at least m nodes in the vertex cover in order to cover all m edges from the matching. Okay, and then possibly we need some additional nodes also in the vertex cover to cover some additional edges. Okay, but at the very least, we need to have m nodes in the vertex cover. And so this is why the vertex cover is going to be at least as large as the matching. Okay. All right, so that was the weak duality property. And that's got a pretty simple proof. But there's actually a stronger version of the statement. So this has the name of this Koenig-Igavary theorem. All right, and what it's saying is that the maximum size matching is equal to the minimum size vertex cover. Okay, so the previous statement was saying that any matching is going to be no bigger than the vertex cover. Okay, and this Koenig-Igavary theorem says that these two quantities are actually equal to each other. Okay, so we're gonna both prove this statement, and we're gonna see how this statement allows us to compute a minimum vertex cover. Okay, because we actually so the nice thing is that we actually know how to compute a maximum matching. Okay, and remember that the way we could compute a maximum matching was to phrase the problem as a max flow problem, right? And the way we were going to do the way we did that when we studied max flow was that we start with this bipartite graph, right? And we're going to add two more nodes, a source node and a source node S and a sink node T, right? And then we're going to connect the source node with all of the left nodes in the bipartite graph. And we're going to connect the sink node with all of the, or actually, we're going to make edges from all of the right nodes to the sink node. Okay, so notice that these edges are directed. Okay, and the capacity for all of these source edges are all of them have capacity 1. Okay, all of these sink edges also have capacity 1. Okay. And then we also, so we have these edges between the left side and the right side, right? And so in this max flow formulation, we're going to direct all those edges from the left side to the right side, and we're going to set the capacities of all of them to be infinite, right? So then once we have a setup like this, then we know that if we compute a max flow on this graph, okay, then this is going to produce a maximum matching, right? So I think that was part of what was covered during the first half of the course, right? So yeah, so again, we simply create a graph of this form, right? We compute a max flow on this, and from that we know that the size of the max flow is equal to the size of the maximum matching. Okay, so now let M be the size of the maximum matching. Okay, and we also know from the max flow min cut theorem that the value of the max flow is equal to the value of the min cut. Okay, so now suppose let's let AB be a min cut. Okay, so A is a set of nodes which includes a source node, and B is a set of nodes which includes the sink node, right? And then AB is a cut which has the same size as the max flow. All right, so we can do all of that using the max flow algorithms. Okay, so once we have that, we're going to use this to actually produce a vertex cover. So the way we're going to do that is we're going to define these 4 sets, okay? LA, LB, RA, and RB. Okay, so LA is going to be defined as the left set of nodes intersect this A. Okay, so remember that A was the sort of the left side of the cut, the side that included the source. Okay, and B was the side that included the sink. Okay, so LA is going to be the left side of nodes intersect A. LB is going to be the left nodes intersect B, right? and then RA is going to be R intersect A, and RB is going to be R intersect B. Okay, and now the claim is that if we take S equals LB union RA, okay, then this actually gives a vertex cover. Okay, so so just to make this a bit more pictorial, right? So suppose you well, let me actually draw like a new figure over here. Okay, so yeah, so suppose we had a bipartite graph like this, right? So let's see, let's make some edges. So let's make edges like, let's say like that, okay? And now we're going to convert this to a flow network, right? So this is going to be our source. This is going to be our sink, right? And remember that all of these edges are directed from like the left to the right. Okay, so I'm not going to draw all of them, okay? And then these are the left nodes and these are the right nodes. All right, now we're going to have a min cut. So let's actually like sort of draw a min cut over here, right? So let's say that the min cut is going to be something like this, okay? So let's say that this is the A side of the cut, right? And let's say that this is the B side of the cut, okay? So then what this statement is saying over here is that if we take LB union RA, okay, so what is LB union RA? Well, let's see, what color should I use for that? Let's use a highlighter, okay? So, so LB, okay, so what is this? All right, so I guess I have to, which color should I use for this one? Well, let's use black for this. Okay, so so this here is LA. Okay, because this is the left side of the nodes. I'm sorry, this is LB. Okay, so this is the left side of the nodes intersect the B side of the cut. Okay, so this is going to be LB over here, right? And then RA is going to be this. Okay, so this is going to be this thing here is going to be RA. All right, and this claim is saying that if you take the union of these two sets, right? So here you have two nodes, right? Then this is going to be a vertex cover. Okay, yeah. So I'm drawing this as an example. I'm not sure if this is actually a correct example. Okay, so I just sort of made up a random graph. Okay, so in case this doesn't work out in the future, I'm sorry about that, but anyways, this is just this is meant to illustrate how this algorithm works. Okay, so I'm not sure that this is actually a correct. I'm not sure this is actually the min cut over here. All right, but anyways, let's assume that this is the min cut, right? Then this first claim is that if we take the union of these two parts, right, then we get a vertex cover. All right, so so let's first of all prove this claim. All right. So the reason this this claim is true is because so all we need to do is switch back to red over here. All we need to do is to just consider an arbitrary edge, and we need to make sure that the set S is going to cover the edge. Okay. So so if U, for example, is an LB, right, then the edge is covered. Okay. Or if V is an RA, the edge is also covered. Okay, so in fact, the only way for UV not to be covered by S, okay, is if U here, right, if U actually belong to LA, okay, then it's not being covered by LB, right? And if also V belong to RB, right, then it's not being covered by RA, right? So if both of these are true, okay, U is in LA and V is in RB, right, then UV would not be covered. Okay, however, it's actually impossible for U to be in LA and V to be in RB, okay? Because if U is in LA and if V is in RB, right? So what that would mean is, for example, let's see. So, you know, if U is in LA, okay? So U is one of the left nodes, right? And if it's in LA, right? And if V is in RB, right? So this, let's say, is U and that's V over here. Okay. Now, this is not possible because if you have an edge like this, okay, so remember that all of these edges are directed from the left side to the right side, and all of them have infinite capacity. Okay, so that's how we design the flow network, right? So this, this edge over here actually has infinite capacity. Okay, but then that would mean that this cut, right? I mean, you see that this edge actually crosses the cut because it goes from the A side to the B side. Okay, so it actually crosses the cut and it's got infinite capacity. So that would mean that the min cut actually is infinite. Okay, but we know the min cut is not infinite because we know that the let's go back to red over here, right? We know that the min cut is equal to the max flow, which is equal to the maximum matching, which is of course finite. Okay, so that means that we cannot possibly have an edge going from LA to RB. Okay, so these edges do not exist. And so therefore, either U is going to be in LB or V is going to be in RA or both, right? And so in either case, in all cases, then this edge UV is being covered. Okay? All right, so this shows that for any edge, right, if we take this LB union RA, it's going to cover all edges. All right, okay, then for the, so let me actually erase this stuff now because we know that this cannot happen. All right, well, anyways. All right, okay, so then for the next part, right, for claim 2, the claim is that this S, okay, defined as LB union RA, is actually equal to the size of the maximum matching, okay? So the reason this is true is because by the max flow min cut theorem, we have that M, right, is equal to the capacity of the cut, okay? And also, what is the capacity of the cut? Okay, so we know that M is equal to this capacity, but you see that the only edges which contribute to the capacity are these edges that go from S to the left-hand side, right? So for example, it's actually, if you look at this edge, right? So this is going from the A side to the B side. So this contributes to the capacity, right? In fact, it contributes 1 to the capacity because we set all these capacities to be 1. Okay, and likewise, if you take a node from the right, right, going to T, right? So for example, this edge over here, okay? So this is also going to contribute a capacity of 1 to the overall capacity of the cut, okay? And now we know that there are no edges of this form, right? We've already seen that because those would have a capacity those would have infinite capacity, which we know doesn't exist, right? And we could have these edges of this form, right? But this is going from B to A, right? So when you have an edge from B to A, it doesn't contribute to the capacity of the cut, right? Capacity of the cut are the edges from A to B. Okay, so we can ignore this this edge over here. Okay, so that means that the only edges which contribute to the capacity are from S to these left side nodes, right? And from these right side nodes to T. Okay, and how many such edges are there, right? Well, we have LB nodes on the left, right? So then these edges of this form, the edges of form SU contribute LB, right? And the edges of form VT contribute RA, right? So these guys, we have we have RA of these nodes, okay? And each one of them contributes a capacity of 1 to the cut. So therefore, the overall capacity of the cut is just going to be equal to LB plus RA, okay? And of course, LB plus RA is equal to S, right? Because S is just defined as their union, okay? And so this thing equals the capacity, which equals M, right? And this also equals S. And so this shows that the matching equals the cover, okay? And this also shows that this S here is the minimum cover because we know from previously that the matching is always going to be at least less than or equal to the size of the cover, okay, right? So we saw that the matching is always no more than the size of the cover. And here we've actually found a cover which is equal in size to the matching. So this means that this cover must be the minimum cover. Okay, so again, the algorithm is just that we compute this max flow to find the max matching, right? And then we define this to be our S, and this is going to be a minimum vertex cover. Okay, so so this is all we have for this lecture. For the next lecture, we're going to look at some local search algorithms. Okay, so local search is another way that we can that we have of sort of dealing with these intractable problems that we nevertheless want to solve. Okay, so then see you guys next time.